some daily life machines that you see. To give an example, suppose I'll keep it easy. Let's say you have an even number and an odd number. You know this that if you add a 1 to an even number, it becomes odd. If you add a 1 to an odd number, it becomes even. And if you do not add anything or basically add a 0, then it remains the same. Diagram is how you try to model this automatons in automata theory. Hey, since I spoke about the automatic doors, let me also try to draw. So by C, I mean closed state, and by O, I mean the open state. So let's say you're in front of this door and you are on the front rear pad. So it goes from the closed state to open state to let you in. Or those pads. Then if it was open, it will automatically go to the closed state. Again, if you're on either of those pads and it was in the closed state, it will remain in that state. If you're still on the front pad and it was open, it will remain in the open state. These kind of small machines that take a very small input and then decide what state to be in based on that input, whether to change their state or whether to remain in the same state, etc. Fourth, what an automata is. So I'll start by this thing called deterministic finite states. So for this kind of a sliding door kind of machine, this closed and open are your states. This kind of a thing, this even and odd are your states. You can have multiple states. It's not like you can have just 2 states or 3 states. You can have quite a large number of states. As long as it's finite, we are fine. Symbol is used to denote the finite set of alphabets. So, what do I mean by alphabets is the thing that it takes as input. Like, for example, this machine, it takes a 1 as input or a 0 as input. So for this one, it will be equals to 0 or 1. Important part. And which we call the transition function. Does is it takes the state in which the machine is at that particular point of time. And it takes an input that comes to the machine and then outputs a state in which the machine will go after taking that input. So to make it make more sense, in here, let's say I am in this Q even state and I take as input a one. So I go to a Q odd state. Or maybe I'm in the Q even state itself and then I take a zero as input. Then I remain in that state that I was in. So Q naught is a state in Q, which we call a start state. Like for any machine to work, at the very beginning, it needs to be in some state that it starts from. Like the like the default state that it is in. So that we call the start state. The last but not the least is F, which is a subset of all of these steps, and this F contains of all the except statements. So, what do you mean by an except state? Well, let's take these examples. Let's say this closed state is the start state for us. By default, it is in the closed state. And then I want to enter, so I want it to open. So when it opens, it goes into an accept state and it changes its state and it opens the gates for me and I can pass through. So here in this case, this is my accept state. But there might not be just one accept state, there might be multiple. Now, slight deviation from real life examples and move to the more generic idea of which is automata. Let me start with giving an example first. Maybe I'm generic one. So let's take this BFA for example. Here my states are Q1, Q2, Q3. One. Well, I'm not writing the transition function. It can make sense of it because if the input is Q1, sorry, if the input is zero and the state is Q1, then it comes back to Q1. If the input is one, you go to Q2, so on and so forth. The start state will be your Q1. So we use this kind of a symbol to represent the start state in the diagram. And then your final state here is again a single state Q2. So the purpose of kind of this finite automaton is basically to accept some kind of string of input and then perform a certain task when it encounters such kind of a string. So for example, in this case, uh, Uh, so in this case, this finite automaton accepts this kind of an input. So all of these 0 star, 1 star, these are basically, there can be a single occurrence of zero, two, three, four, multiple occurrences, or no occurrences of this. So for example, if I have just one, Q1 goes to Q2 and it's already accepted. And no matter how many zeros I have, be it 0, 1, 2, 3, 4, 100,000, it does not matter. Q1 comes back to Q1, and then one single one takes it to Q2. And then again, multiple ones does not make any difference. One single zero. So a pair of zeros takes Q2 to Q3 and back to Q2. And then again, if there's a zero and then there's a one back, then you come back to Q2. So basic purpose of our finite automaton. A certain string and then perform an action based on it. Uh, Before that. So let's name this DFA, let's say D1, and let's name this kind of strings, let's say L1. So we say that D1 accepts L1 if this string L1 can take the automaton D1 from the start state to an accept state. And then like it accepts all the strings in L1, and L1 is called the language of it. And we are dealing with finite automatons. So a definition which might not be of use to you now, but within the next 15 to 20 minutes, it will be. So just look for bookkeeping. Language is called regular language. If line of the steps. So now, okay, maybe before this, we'll explore this. Yeah. So I have a question for you. Tell me example of at least one string that this finite automated will accept. Real string. Because 0, 0, 1 it accepts. Give me something else. If you can give me the general string, it's even better. Yeah. Am I audible? Yeah. Yeah. So I was asked that once. That was okay. So for Shreya, the question was that what kind of a string will this finite automaton accept? That is, what kind of a string will take it from the state few to this few sub 0, 0? Yeah, so as you can see in any case, whatever string this accepts, it will only accept string that have a substring 0, 0, 1. If not, it won't. Often than not, you have a very simple description of what kind of a string it accepts. But, well, not all simple things can be, you know, written formally and shown formally to be accepted. Like, for example, if you have something like this, and in many occurrences of one. Well, in those cases, you cannot get a finite automaton that accepts this string. And in such cases, these are called non-regular languages. Well, one common mistake or one common idea that people come up with is basically, let's say you have some state Q1 and state Q2. Yes, and this is the exception. But this takes you to 0, 1 to the power n rather than 0 to the power n or 1 to the power n. The problem with this is that a finite automaton, as I started with, is basically used to represent these finite machines, which have finite memory. So it's not like it can keep track of how many zeros it has taken. Like how many zeros have appeared till now. Well, maybe till a point, okay, it can. But what if you have 100 zeros and then you want it to be followed by 100 ones? So in those cases, you need to have a bypass such that you can read these kind of languages. And that's where these non-regular languages come. But I'll come to that a bit later. Before that, some common things called regular operations. So let me start by setting the terms. So let's say there's some language L1 that is accepted by language T1, that is accepted by the automated D1. And there's some language L2 that is accepted by the automated D. Now, some things that you can ask is, you know, give me an automaton, say D3 that accepts L1 union L2. Okay, give me an automaton that accepts, say, L1 is L1 for X. So L such that X belongs to L1 from Y. Or maybe you can ask a star kind of thing. Uh, some L1 star.
So your voice is tumbling.
Hello, sir.
Yes, now okay, sir. So can you please repeat after D2 and D1 part? D3.
Yeah, sure, sure. So take L1 to be a language that's accepted by the automated D1 and L to be a language that's accepted by the automated D2. And you are given the task of creating an automated D3 that accepts uh, any of these regular operations performed on L1 and L2. So maybe L1 union L2. That is, some string that either belongs to L1 or belongs to L2. And whatever the case might be, it's accepted by this D3. Or maybe some XY where X belongs to L1 and Y belongs to L2. And you just glue them together. Or maybe some L1 star, which is from K many occurrences of X glued together where X belongs to L1. So all of these are called regular operations. And to deal with these, we come up with something, well, to be very honest, to deal with this using a DFA, it becomes very messy. It's not hard, it's intuitive, but it's very messy because what a DFA tries to do is in these transition functions, it accounts for all of the alphabets and all of the states, and that makes the entire diagram, like the automated diagram, pretty messy. So, thus we come up with something called an NFA, which is deterministic. So, let me give the definition of this first. So again, this is also a 5 tuple in which Q is the finite set of states. This is the alphabets. This is the start state. This is the final state. This is what changes. So now this becomes a function from the present state. Let's say some Qi. The input, let's say some A value to the power set of Q. And okay, now I mean, some set belonging to a positive, maybe something like UI1, and this A belongs to you all know are the alphabets. Is basically an empty string, or let's say empty alphabet. What that does is basically it lets the finite state automaton to move a step forward without ever taking any input. In this case, a few things that you will notice are different from a DFA are the existence of this epsilon, one. Second is if you are in state Q1, an input one can keep you in Q1 or take you to Q2. Precisely this taking place, that is the transition function taking you to a element of the power set of Q. And you would see that I have an input one and the present state is Q2, and it takes me to no state whatsoever. So that is basically it taking to phi. Phi is also an element of the power set. So that should make sense to you from the transition, from the change definition of the transition function. Yeah. So in this case, is this is a string that is accepted by this automaton. So, innumerable number of zero, innumerable amounts of number of ones. Then just one takes you from Q1 to Q2. And yeah, a zero takes you from Q2 to Q3, a one takes you from Q3 to Q4, and then you can again have as many zeros and ones as you'd like. But accepted. This is also a string that is accepted. One. Because, as I said, epsilon is an empty alphabet that lets the finite state automaton to move a step forward. So once at this point, once you reach Q2, it can take the empty alphabet, move itself up to Q3 without taking any, proper alphabet as input. And then it can take Q3 to Q4 using this. Epsilon gets very useful and it ultimately allows us to get an automaton that deals with all of this. Once this is clear, the rest of the construction for all of those is affected by D1 and this is accepted by D2. I'm not taking any examples of these D1 and D2. Let this be a black box for D1 and this be a black box for D2. So, I mean, essentially, let imagine that there's an automaton here that accepts this language L1 and an automaton here that accepts this language B, L2. Now, if I assign, let's say I make this Q my start state. I take this to be my new NFA. Then, as soon as it goes to the start state without taking any alphabets, it can take the empty alphabet and move on to the start state of D1. Similarly, it can move on to the start state of D2 from there. And then within those black boxes, it checks whether it can reach the final states in either of them. So now, let's say for D1, your states were Q1, if this whole thing is your D3, those becomes a final one. Function changes is the transition function takes q comma epsilon to the set q1 comma q2. And it takes q1 So basically, as soon as the transition like this automaton enters this D1 automaton, the transition function for this D3 starts behaving as this del1, and if it enters D2, it starts behaving as del2. Now, if you are trying to concatenate, so let's say L1, L2. Again, L1 accepted by D1 and L2 accepted by D2. So let me say that this is my D1. And maybe these are some of the final states of D1. So the way you construct D3 that recognizes this concatenation of the two languages is basically silent string or an empty alphabet takes the final states of D1 to the start state of D2. The start state of D1 becomes your start state for D3. The final states of D2 becomes the final state of D3. The states are Q1 union Q2. The alphabet is this. The transition function delta. Your start state is Q1 corresponding to D1, and your final states are F2. How does the transition function behave? Well, inside D1 it behaves as del 1. Inside D2 it behaves as del 2. But for the cases where you are in the final states, F1 or final states cross epsilon, it takes it to Q2 necessarily. For anything other than epsilon, it keeps on behaving like L1. Regular operations, I have showed you how this will look. Uh, D1 accepts L1. Accepts L1. L1 star is basically, well, it can have the empty string or multiple occurrences of x1 through xk, where each of these xi's belongs to L1. And in case rectangle, the T1. Yeah, so this is your D1. These are the final states of D1, say. This is the start state of D1. There are multiple transition functions, but what are the transition functions that you must include, and what are the start states that you must include in order to accept this kind of a language? Can anyone answer? Any ideas? A guess, even if you're wrong. Well, you get a habit of trying. So in such a case, what you try to do is change the start state to something like this. Some here. The start state is also the final, also one of the final states. Why? Well, because L1 star can accept the empty string, so it's needed. Start state, if you go to the final state once somehow, that's one occurrence of x1. You roll it back to the start state again, and the process continues. The second occurrence, the second time you reach the final state, and so on and so forth. So till now, TFA, you can say, helps us those strings to be identified. In FA, with the use of taking one input can take you to multiple different states, or even not taking an input can take you to other states. Multiple if it is or anything. Now, something that I mentioned was this kind of a thing. As I said, it has finite memory, so it can't keep track of all the zeros that it has encountered and then cross check that the number of ones is the same. So it needs to do something to deal with this kind of a problem. As it turns out, it needs to use some amount of memory. Can't argue about that because, but we try to bring it down using something called CFGs or context-free graphs. Again, starting with the very formal definition of it. In using its formal definition. Uh, so this, so these are called substitution rules. So basically, you have a long string of these A's, B's, zeros, and ones, and of these left-hand side stuff with the right-hand side stuff. The first element that occurs in the first substitution rule is basically your start element. These A's and B's are your variables, and these zeros and ones are your terminals. So mind you that you can, in substitution rules, you always replace variables and not terminals, because terminals are fixed inputs, but these variables are not. They can be a single alphabet, it can be, or it can be multiple alphabets clubbed together. So, like, for example, if we are taking this substitution rule and breaking it down, then maybe we start with an A. Replace it with a 0, A1. Now, okay, we're gonna tap on to with an A. Now we have two choices. We can either replace it with a 0, A1 or a B. I choose to replace it with a 0, A1. Again, same choice. A with a B or A with a Z over 1. I'll make the same choice again. Maybe the next step I can make the same choice and maybe I can replace the A with B. Maybe I do that. Maybe I replace the A with B. Now, the only substitution for B that is possible is this hash kind of thing, which essentially is an empty string. So what it comes down to is 0011. But it have had multiple like multiple things. It could have been decoded to anything of the form. Okay,
Zero and one and
did anyone say something? Yeah, so if we repeated this over and over and over, we would have reached at some point to a 0 to the power n, a 1 to the power n, which after that step, maybe we made it to 0 to the power n, b 1 to the power n, and that gets decoded to 0 to the power n, to the power n. Exactly the thing that we needed. In terms of the rules, while it may not appeal too much, but so maybe for this derivation, if I draw the tree for so yeah, we omit the first variable, and this is the first step that we come in. So 0 A1, we decode the A to be 0 A1, then the A to be B, and then the B to be this hash. And thus we reach at this kind of a decoded value. So yeah, for the formal definition of a CFG is a full tuple. Variables. These are the same alphabets, but from now, in the context of CFG, we start calling them terminals. R is what we call rules or the substitution rules, and S is our start variable. Let me just quickly give you guys a sneak peek into something else. So, okay, automata theory is more of a theoretical CS construct. It's not very widely used by mathematicians, but there's something that directly corresponds to this. Is what we call Markov chains. Well, what are Markov chains? Now that you know the definition of an automata, well, let's not get into this CFG stuff for the Markov chains now. Let's stick to this DFA kind of stuff for the ease of use. So the Markov chains, what you do is take a DFA, add a probabilistic angle to it, and then what you have is a Markov chain. Might be vague, let me explain. Uh, so I go back to this Q even and This was our automata. Now, if we add a probabilistic angle to this, like for example, you have a coin and you toss it, take an unbiased coin for now. So you toss that coin. If you get a heads, yeah, okay. Maybe you are in a casino where there's this kind of a game that gives you a coin. If you toss the coin and if head comes up, then uh, the casino gives you 1 rupee coin, and if a tails comes up, then it gives you nothing. So if a heads comes up, you're winning. So at the start, it was few even because it was zero. Uh, so if a heads comes up, you add a coin. A heads comes up against you add a coin, and so on and so forth. And if it's a tails, then for that round you win nothing. So now the probability of heads coming up in an unbiased coin is half. The probability of a tails coming up in an unbiased coin is half. Then this is a finite automaton and not a Markov chain yet. The reason being that all the probabilistic stuff is happening outside this. It takes a heads or a tails as input strictly even now. It's just that the alphabet has changed from 0, 1 to H and D. But now what you do in case of a Markov chain is you no longer care about these alphabets or these inputs, but rather you directly care about this probability. That is to say, all this probabilistic stuff, all the deciding what the input is, that does not happen outside this automaton, but happens within it. And that's what converts this finite automaton to a finite probabilistic automaton, which you also call a Markov chain. Common modeled using Markov chains is random walks. So I'm stating this strictly as an example. I won't be modeling a random walk using a Markov chain. It's just a sneak peek into Markov chains. Maybe in some of the upcoming talks, maybe you get a chance to see what a Markov chain is. If not, you can just simply do a Google search and you'll get from it. So random walks, let's stick to 1D. You are standing at this point 0, and there are all these integer coordinates. So there are all these integer coordinates, and if you like starting from 0, if you toss a coin, if you get a heads, if you are position I at that point, you go to I plus 1. If you get a heads, and you go to I minus 1 if you get a tails. Strictly bothered about whether after a certain number of steps you will stay at a even integer coordinate or an odd integer coordinate. Then if you stay at the same step, then this is the exact Markov chain that you are dealing with here. But let's say you're not bothered with that. Let's say you want to deal with the entire thing. So let's say q sub I is the integer coordinate that you are at that point of time. So there when you go back. So you go to the minus one with the probability half. You go to q sub one with the probability half. Then you go to q sub two with the probability half. You come back to the probability half. But so on and so forth. Yeah, but of all of these, two important concepts in Markov chains are these things that people normally are bothered with are recurrence and transience. So, yeah. So here, let's say you start at Q0. You do a coin toss. You either go to Q2 or Q1. Now, no matter what the coin toss comes up to be it heads or be it tails, there is no chance that you are coming back to Q0 at some point. So you call Q0 in state. Now let's take Q1 for example. Let's say rather than Q0, you're starting at Q1. Q1 will be called a recurrent state because if you start at Q1, then you just either stay at Q1 or go to Q2, stay at Q2 for some time and then come back to Q1. So after infinitely many steps, you will come back to Q1 no matter what. So Q1 is called transient state does not always necessarily mean that you will never come back to that state. It just means that there's a non-zero probability of you not coming back to the step to that state after infinitely many steps. Like for example, if there was say another state here Q3, so there's a third by half to the power n chance that after n, yeah, after n plus one many steps, Q will come back to Q. But then if you sum this over all such n, you will find that this comes out to be less than 1. So as long as after n many steps, the probability of you coming back to that state is less than 1, then we call it a transient state. Again, this was a sneak peek. This was not very formal, but yeah, the idea of Markov chains comes very directly after what we call automata once you introduce a probability. Okay, it's already kind of very close to 6, so maybe I'll stop here. Any doubts, any questions? Like any unified list of frameworks about common algebraic model. starters, uh, I would okay. Markov chain is a like immediate next step of a DFA because you just add. Okay, so maybe it's better. Okay, take Markov chain in the first thing, and then you separate the probability and the automata out. Like basically, you do all of those probabilistic stuff outside of this entire transition graph that you have. So, what I'm calling a transition graph. So, all of this probability business that's happening, you make it happen outside of this transition graph. Uh, with each of these probability, you basically take an input, and then based on that input, you decide the next step. That's how you get a DFA from a Markov chain. And from a DFA, you just add the probability in and you get a Markov chain. So it's very like one and the same thing, adding the probability or removing the probability. That's all. And for the part where the two frameworks can, there's no kind of, well, formally, when we say unifying two frameworks under a common model, it basically means that they are two completely different things. But Markov chains and DFA are not that different. It's just whether you're doing the probability calculations outside the transition graph or inside the transition graph. That's all. As for the common algebraic model, well, there are linear algebraic methods to model like this Markov chains. Like for example, if you are trying to model this using linear algebra, you would just go on and do this. Yeah, so you basically input this entire structure into this matrix. DFA that accepts only the empty string and the DFA that accepts nothing at all. Well, it's one and the same. DFA accepting the empty string is basically a DFA that accepts nothing at all. There's it's more of a language difference than the conceptual difference. So this is a DFA that accepts nothing at all. DFA that accepts an empty string as well as this accepts the empty string. This also accepts the empty string, but this accepts stuff other than the empty string. This does not. So yeah, that is the difference. But other than that, if your question was strictly about an empty input that it accepts, then yeah, it's one and the same thing. Okay, for Shreya and Srijan, are my explanations clear or are there any doubts?